Welcome to the deep dive. So imagine for a second that you hand a $1 million supercomputer this massive, highly structured data set.
Right, expecting absolute brilliance from it.
Exactly. You expect brilliance, but the whole system just, well, it effectively crashes. And why? Because it didn't know how to type a single hashtag.
Yeah, it's basically the ultimate paradox of modern AI, you know?
It really is.
We have these massive models that can, like, pass the bar exam or write complex software architecture, but when you ask them to format a basic business address, they just stumble.
Or they hallucinate entirely.
Right, or they take 2 minutes to give you an answer. And if you're trying to automate data collection at scale, those failures don't just cost you time, they cost an absolute fortune.
And that is exactly what we are unpacking today. We've got our hands on the documentation of a really fascinating internal experiment.
Oh, this study's so good.
It's incredible. The engineers behind this test took 13 different AI models. We're talking heavyweights, right? Like Grok 4.6, Claude Opus 5, Gemini, and Quinn.
The big ones, yeah.
Yeah. And they tasked them with extracting highly specific business intelligence from a real-world physical rehabilitation center down in Australia called Sage Active Clinic.
Which, by the way, serves as a brilliant microcosm for this whole issue.
How so?
Well, because extracting data from a local business website sounds simple, but it actually exposes the hidden mechanics of how these models work,
Right.
like how they distribute their cognitive budget.
Right, between reading text, obeying formatting rules, and actually understanding the strategy behind the business.
Exactly. It's a balancing act for the AI.
So today we're going to explore why simple instructions break million-dollar models and how tweaking a prompt acts like a competitive intelligence microscope.
A very expensive microscope.
Seriously. And finally, we'll reveal a brilliant two-stage split pipeline architecture, one that completely decouples raw data retrieval from strategic synthesis.
The math on that pipeline is wild.
Oh, it's game-changing. This specific architecture cuts AI costs by 55% and execution latency by an incredible 95%.
It's massive.
Okay, let's unpack this. Starting with the first major hurdle the engineers ran into. They called it the split brain defect.
Right, the split brain defect. This failure is just a perfect window into how an AI actually processes instructions, you know?
Break down what happened.
So the engineers gave the models a very explicit rule in the text of the prompt. They said, start the output directly with a level 1 markdown heading.
And just for anyone listening who isn't a coder, in markdown formatting, that just means typing a single hashtag, right? Followed by the words extracted business data.
Exactly. A single keystroke. It sounds completely foolproof.
But out of the 10 models tested in that first run, 8 of them completely failed to do it.
8 out of 10. And the reason why is almost comical, actually.
It really is. The prompt had a built-in contradiction.
Yeah, a massive one.
The written instructions in the middle of the prompt said, use the hashtag.
Yeah.
But at the very bottom, the engineers had pasted a visual template of what the final output should look like.
And in that template, somebody accidentally left the hashtag out.
Oops. Just a tiny human typo.
Right. But for the model, it receives conflicting orders. But what's really revealing is the mechanism behind how it resolves that conflict.
Like how it decides which rule to follow.
Exactly. When an AI model processes a prompt, it utilizes attention mechanisms to weigh the importance of different pieces of text.
Yep.
And these models are fine-tuned by their creators to heavily prioritize structural templates and code blocks located at the absolute end of a prompt.
Way more than the narrative text written in the middle.
Right. The attention heads essentially calculate, well, the human wrote a story up there, but this strict visual layout down here at the end, that must be the final ground truth.
Wait, let me challenge that for a second. Are we saying the model completely ignores the written text? Or is it trying to merge them and just failing?
It's a good question.
Because it's like giving a brilliant Michelin-star chef a recipe card with a typo at the very bottom. Do they just blindly follow the typo?
Well, they don't ignore the text entirely, and that's actually the problem. To build on your chef analogy, the chef reads the recipe, gathers all the ingredients, starts prepping the dish,
Right.
and then looks at the final photo on the card and realizes, wait, this picture doesn't match my prep work.
Oh, no. So they panic.
Exactly. So the chef throws out the prep work and desperately tries to plate the dish to match the photo.
Wow.
In AI terms, the model calculates the logical path based on the text, hits the visual template at the end, realizes there's a contradiction, and discards its initial token generation plan.
And just defaults to the visual structure.
Yes. And to make matters worse, it's fighting its own native biases at the same time.
Wait, native biases, you mean how it was originally trained?
Precisely.
Yeah.
Because these models are trained on billions of documents, they naturally treat a single hashtag, a level 1 heading, as a global document title.
Like the title of a book.
Right. But in this prompt, they were being asked to generate a nested data profile.
Ah, I see.
Their native training aggressively biases them to use a level 3 heading, which is 3 hashtags, for nested data.
So they are fighting the visual typo at the end of the prompt, and they are fighting their own foundational training about how documents should be structured.
Exactly. They are caught in a complete cognitive crossfire.
Now, there was one exception in the source data. Grok 4.6 actually got it right.
It did, yeah.
It somehow had the multi-step reasoning power to override the visual template at the bottom, ignore its native bias, and strictly follow the text rule in the middle.
Which is impressive.
But, and this is a big but, the latency was brutal. It took an agonizing 131.7 seconds to generate the output.
Over 2 minutes.
Yeah. If Grok is so smart, why didn't it just instantly realize the visual template was a typo and move on?
Well, because resolving contradictions is computationally expensive.
Oh, burns compute.
Tons of it.
Yeah.
It requires the model to allocate a massive amount of its compute budget to self-correction and internal validation before it outputs a single word. It's running multiple probability trees, comparing the conflicting instructions, and deciding which rule takes precedence.
Taking over 2 minutes to extract a few paragraphs from a single website is completely unworkable at scale.
Right. Raw reasoning power is impressive, but if it drains your compute budget just to format a header, I mean, you're losing the game.
Which brings us to a really fascinating pivot. Because if an AI is burning all its cognitive energy just trying to place a hashtag correctly, does it have any brain power left to actually understand what the data means?
That is the million-dollar question.
Because the AI you choose doesn't just dictate your server costs. The sources show it fundamentally changes the soul of the data you extract.
This qualitative analysis was arguably the most critical part of the experiment. Let's look at the actual business they were analyzing, Sage Active Clinic.
Okay, let's look at them.
It operates with a very deliberate brand tension. On one side, it is a highly credentialed clinical environment. They employ accredited exercise physiologists. They utilize advanced clinical diagnostics like in-body 770 scanners. I mean, it is serious medicine.
Right. But the flip side is that the owner specifically designed it to be a mirror-free, welcoming, anti-gym environment.
Exactly.
It's built so that older adults or people dealing with severe chronic pain don't feel intimidated the second they walk through the door.
Yeah, that's crucial.
It's a medical clinic, but it's supposed to feel like a warm neighborhood community.
Exactly. And when the engineers task the AI models with synthesizing this specific brand identity, the models fractured into 3 distinct cognitive profiles.
Okay, what was the first one?
First, you had the models acting as strict therapeutics. Gemini 3.7 Flash fell squarely into this category.
Interesting.
It leaned heavily into the medical side, defining the brand tone as clinical, supportive, and empowering.
Which, I mean, isn't technically wrong.
Yeah.
But it sounds like a sterile hospital wing.
Right.
It completely scrubs away the neighborhood family vibe. Why would a highly advanced model like Gemini default to such a cold tone?
It comes down to safety fine-tuning. Models that are heavily optimized to avoid hallucinations and maintain factual accuracy often default to a sterile academic tone.
Because it's safer.
Exactly. They prioritize the verifiable clinical terms over the nuanced emotional context, because emotional context is much harder to mathematically prove.
That makes a lot of sense.
But then you had models that fell into the balanced clinician's profile. Grok 4.6 absolutely nailed the owner's true intent.
What did it say?
It defined the tone as warm, supportive, and clinically professional. It successfully held both of those concepts in tension.
Wow. And this wasn't just about picking better adjectives for a brand summary, right? The prompt actually tested their strategic business logic.
Oh, yeah. It went way deeper.
It asked the models to identify a value transformation. Essentially, what is the ultimate barrier stopping someone from coming to this clinic, and how does the clinic solve it?
And here is where the analytical biases really showed. A large chunk of the models identified a methodological barrier.
Meaning what, exactly?
They concluded that the main problem for this demographic is the fear of unsupervised exercise risking re-injury, and the clinic's solution is clinical tracking.
I mean, academically, that's true. If you're injured, you fear re-injury.
But Grok 4.6, acting as that balanced clinician, went deeper. It identified that the ultimate barrier for these specific patients isn't just the physical pain, it's financial.
Now, I have to jump in here. Are we sure Grok actually understood the financial barrier?
What do you mean?
Well, did it just scan the website, see words like Medicare and seniors, and probability match them because they frequently appear together in its training data? How do we know that's actual strategic synthesis?
It's a great question. We know it's synthesis because of what Grok connected it to. In Australia, the National Disability Funding Program, the NDIS, and Medicare, they have complex rebate structures.
Right.
Grok didn't just parrot the word Medicare. It analyzed the clinic's specific target demographic, older, mirror-reverse adults with chronic conditions, and synthesized that for this specific group, the high out-of-pocket cost of specialized care is the actual gating mechanism.
Oh, wow.
It mapped the community warmth to the financial accessibility. It understood the business model, not just the vocabulary.
So if you're the listener and you're using AI to extract data to build a massive CRM or automate a sales email sequence, this is vital.
Absolutely.
Choosing the wrong model means you might blast your prospects with cold, clinical hospital jargon, completely missing the fact that their real anxiety is financial.
Right. The model you select acts as your brand's voice and your strategic lens.
Precisely.
Yeah.
Which is why the engineers realized they couldn't just accept these disparate results. They needed to force all the models to look closer.
So they rolled out version 2 of the prompt.
Right. They fixed the broken visual template, they added the missing hashtag, but they also made the instructions significantly harder.
Much harder.
They added granular rules, forcing the models to dig for specific contact info, like the website URL and phone number. And they set strict fallback logic, like if a mobile number isn't found, output none found on website.
Yeah, very specific constraints.
They also enforced tight formatting constraints, like keeping bullet points strictly under a 10-word limit.
This revised prompt effectively acted as a competitive intelligence microscope. By mandating strict retrieval rules, the models could no longer just skim the high-level homepage marketing copy.
They had to really dig.
Exactly.
Yeah.
They were forced to scour the deeper, specialized operational pages of the site.
And it paid off brilliantly in terms of discovery, right? Grok 4.6 and Qwen 3.7 Flash dug deep into the pricing and billing pages and discovered WorkCover, which is a state worker rehabilitation fund.
Right, a key revenue channel.
And that wasn't captured anywhere in the first run, but there was a massive catch.
Yeah, the cognitive complexity cost.
Exactly. By adding these granular rules and validation checklists, some of these models absolutely choked.
They hit a complete wall. GLM 5.2, which is blazing fast on the first prompt at exactly 1.0 second, slowed down by a factor of 10.
10 times slower.
Yeah, it dropped to 10.1 seconds. GPT 5.6 Luna slowed down by 2.8 times.
Wait, help me understand the mechanism here.
Right.
Why does clarifying the rules make them slower?
Think about how they generate text.
Because if you tell me exactly what you want, like keep bullet points under 10 words, shouldn't that be easier to execute than a vague instruction?
For a human, maybe. For a large language model, it requires an immense amount of token generation planning. An AI generates text token by token.
Right.
When you impose a strict 10-word limit on a bullet point, the model can't just start talking. It has to calculate the token lengths and its hidden states, plan the entire sentence structure, check it against the word count constraint, and verify the missing mobile number logic.
All before it outputs the very first character.
Exactly. That logical overhead consumes its compute budget in the planning phase, which is why your latency spikes.
That makes perfect sense. But looking at the data, there was one wild exception to this rule.
Oh, Qwen.
Yeah, Qwen 3.7 Flash actually got faster with the harder prompt. Its execution time dropped by 4.2 seconds. How is that even possible?
Because of what the engineers removed. Remember, version 2 of the prompt fixed the visual contradiction, that missing hashtag.
Oh, right.
For Qwen, removing that contradiction removed its structural confusion. Its underlying processing speed stayed the same, but its token attention mechanisms no longer had conflicting weights between the instruction layer and the formatting layer.
So to go back to our earlier analogy, it's like driving with a broken GPS.
Yes.
Even if you have a ridiculously fast sports car, If the map keeps recalculating and giving you contradictory directions, you have to hit the brakes.
Right.
The moment you fix the map and make it clear, the car stops hesitating and speeds up to its true potential.
Exactly right. Every time it recalculates, it burns compute tokens. Fix the contradiction, and it just sprints.
But here is the ultimate dilemma the sources point to. Even with a perfectly fixed prompt, you still have a fundamental problem.
Yep.
If complex rules slow down premium models like Grok and fast, cheap models miss strategic nuances like that financial value transformation, how do you win?
It feels impossible.
Right. How do you achieve speed, absolute precision, and low operational cost all at the same time?
Here's where it gets really interesting. You stop trying to find one single magical AI model to do everything.
Okay.
You mimic a highly efficient organization you build with the engineers in these sources call the two-stage split pipeline.
This is the architectural climax of the entire experiment, and we really need to highlight this. By splitting the task into stage 1 factual scraping and stage 2 strategic synthesis, you completely decouple raw data retrieval from complex instruction compliance.
That's the secret sauce.
This is the exact architecture modeled in our ROI calculator that cuts costs by 55% and execution latency by 95%. Let's break down the mechanics of this pipeline because this is the core takeaway for anyone listening who wants to build these systems.
Let's do it.
Stage 1 is factual scraping. For this stage, you intentionally use a small, ridiculously fast, and incredibly cheap model.
The sources highlight Gemini 3.5 Flashlight for this.
Right, which runs at a blazing 0.1 seconds or Qwen 3.7. You point this model at the website and you give it one job. Ingest the massive, noisy payload of raw HTML and output literal, verified facts.
Right. You don't ask stage 1 to write marketing copy, and you definitely don't ask it to enforce 10-word bullet limits.
No strategy at all.
None. You just use it to pin the ground truth. Is the address Suite 4, 215 Bay Street? Yes. Is there a mobile number on this page? No. Return none found. It creates a sterile, verified list.
Then you move to stage 2, strategic synthesis. Now you bring in your premium deep thinker model, like Grok 4.6 or Claude Opus 5.
But here is the critical mechanism.
Right, you do not feed stage 2 the website HTML. You only feed it that tiny verified list of facts that stage 1 just generated. Why is stripping out the HTML so revolutionary?
Two massive reasons. First, it virtually eliminates hallucinations. Hallucinations often happen because a model gets confused by noisy background data, like a website sidebar or footer code.
Oh, I see.
Because the Stage 2 premium model has no raw, noisy text to misinterpret, it can't accidentally invent a phone number that doesn't exist. The facts are locked in by Stage 1.
So it's effectively foolproof.
Exactly. And second, its cognitive budget is completely unburdened.
Because it's not reading HTML.
Right. Because Grok 4.6 doesn't have to spend its reasoning tokens reading and comprehending 5,000 words of messy HTML, it can focus 100% of its brainpower on complex instruction compliance.
Wow.
It can easily ensure that every single bullet point obeys the 10-word limit, and it can flawlessly synthesize those deep strategic insights, like the financial barrier we discussed earlier, without getting bogged down by syntax.
You completely decouple the heavy text ingestion from the high-level brand alignment. You let the fast data gatherer gather, and you let the brilliant strategist strategize.
Exactly.
It sounds beautiful in theory, but I want to dive into the actual math from the ROI calculator provided in the sources.
The math is the best part.
Because this pipeline isn't just about making the AI smarter, it completely collapses the cost structure. The exact architecture modeled here cuts cost by 55% and execution latency by 95%.
Right.
Walk me through the mechanism of that pricing. Why is it so much cheaper to use two models instead of one?
It comes down to how AI API providers charge you. You are charged based on input context, the amount of text you feed into the model.
Okay, per word, basically, or per token.
Right. Premium models charge massive premiums for every 1,000 tokens of input. If you feed 5,000 words of website HTML into a premium model, you pay a premium price for all 5,000 words. Got it. But in the two-stage split pipeline, stage 1, the incredibly cheap model, reads the 5,000 words. It compresses it down to a 200-word verified list.
Oh, I see where this is going.
Then you feed only those 200 words to the premium model. You are literally slashing the input tokens the expensive model has to read, which is the mechanism driving that 55% cost cut.
That is absolutely brilliant. The average cost per run drops from roughly 9.5 cents down to just 4.3 cents.
And the speed improvement is just as dramatic.
Because the premium model isn't processing a mountain of text. The average latency, the time you sit there waiting for the final output, plummets from 131.7 seconds down to just 6.0 seconds.
which completely changes what is possible at scale.
Let's contextualize that scale for the listener.
Yeah.
Imagine you are building a massive industry database or a CRM, and you need to run this extraction process on 100,000 different business websites.
If you try to do that with a single-stage premium model, the math is brutal. It will cost you over $9,500 in API fees.
Ouch.
And you will rack up 3,658 hours of compute wait time. Your servers are just sitting there burning money, waiting for the model to think through massive HTML files.
But if you implement the two-stage split pipeline,
You save $5,248 in pure cash.
wow.
And more importantly, you bypass 3,491 hours of server latency. That is 145 days of wait time, completely eliminated from your workflow, while actually improving the factual accuracy of your final dataset.
145 days of compute time vanished
Yeah.
just by separating the task of reading from the task of thinking. It's absolutely incredible.
He really is.
So let's bring this all together. We started with the split brain defect, watching a $1 million AI trip over a simple markdown hashtag because of conflicting instructions.
A very expensive typo.
Very. Then we explored how different models interpret the soul of a business, proving that AI selection dictates whether your data sounds like a cold clinic or a warm community.
Right, the cognitive profiles.
And finally, we saw how designing a two-stage architecture, decoupling raw data retrieval from complex instruction compliance, maximizes speed, slashes cost by 55%, and drops latency by 95%.
It really hammers home the lesson that the smartest way to use AI isn't just blindly hunting for the single biggest brain on the market. It's about designing the smartest workflow. True operational efficiency happens when you actually understand the mechanisms of the tools you are using.
Absolutely. But I want to leave you, the listener, with a final thought to ponder today. Think about that two-stage split pipeline.
Okay.
Splitting AI tasks into a data gatherer and a strategic synthesizer mimics a human corporate org chart perfectly. You have the junior analyst doing the heavy research and the senior executive taking that summary to make the strategic decisions.
It's an incredibly familiar structure. It's how humans have optimized complex work for centuries.
Right. So here's the question. As these AI models become more agentic, more autonomous, and more self-aware of their own compute costs, how long is it before the AIs realize this efficiency for themselves?
Oh, that's an interesting thought.
How long until you ask a massive premium model to read 100,000 websites, and without you even prompting it, it silently delegates the reading subtasks to smaller, cheaper models behind the scenes, just to save itself the cognitive headache?
Now, that is a fascinating and, honestly, highly probable prospect. The architecture we have to manually build today might just be their default behavior tomorrow.
We might not be the only ones optimizing org charts for much longer. Thanks for joining us on this deep dive into the hidden mechanics of AI extraction. Catch you next time.